This is Algebra 2 with Trig, 1D.1a. We are going to solve systems of equations graphically. A system of equations consists of two or more equations. You've got to have two for them to possibly intersect. So we're going to have two or more equations. The solutions of this system is where the graphs intersect. When solving a system of equations, there are three possible scenarios. These are linear system of equations. There are three possible scenarios. You're going to cross at one spot where two lines cross. Happens a lot. If they're parallel, that means the slopes have to be the same, but the y-intercepts could be anything. That doesn't happen a ton. And then for the equations to be exactly the same, the slope is the same and the y-intercept is the same, they're going to be the same exact line. That means every point that works in one equation will also work in another equation. This one tells us that any xy that works in this equation will not work in this second equation. There are no solutions in parallel. And with two linear equations that cross at exactly one point, there's an infinite number of x's and y's that work in this equation or that work in this equation, but there's only one that works in both equations. When we graph our equations, the lines intersect. The slopes are going to be different. That is what we know about two linear equations that intersect, that have a solution. The lines are going to cross and the slopes have to be different. In this case, when we graph parallel lines, the lines do not intersect. The slopes are the same. The slopes are the same slope. So for this one that's up and over, up and over, up and over, this one's going to be the exact same slope. Rise over run. Same slope. And when we graph, the lines are the same. They coincide with each other. The slopes are the same, and the y-intercepts are the same. It's the same line. Usually one of your equations is a multiple of the other one, so after you simplify it down, then you find out that it's the same. It doesn't necessarily look the same right away. Here, the slopes are the same and the y-intercepts are the same. Sorry, they're not the same. The slopes are the same, but the y-intercepts are... What happens in parallel about the y-intercepts? They're different. Okay, so we're going to come down here and try to graph these two system of equations. This equation is written in y equals mx plus b form. That's usually the form people prefer it to be in. And then Our second equation is written in a standard form of a linear equation. It's kind of like a circle where you have the x's and y's on the same side of the equal sign. But here we have coefficients, we don't have squares, it's definitely not a circle. But we have our x and y on the same side and our constant on the other. So let's take this first equation. There's nothing we need to do with it. The b value, which is the -2, is your y-intercept, so we're going to start at -2. And then we're going to do our slope of -3, +1. Or +3, -1. +3, -1. And we connect those dots together, and we have our equation. Now we come down to our second equation. Our second equation is not written in that form. So if we want to convert it into that form, then we're going to need to subtract over our 5x and divide everything by 2. And there is our new equation. It's equivalent to this one. And see how they look different? But they stand for the same thing. So we're going to be at -1, which almost is touching. Then we're going to do a slope of -5, +2. Doesn't miss my bunch. And then we're going to do +5, -2. Hey, right on it. So even though this one was off by just a little bit down here, you can see that those two lines are just a little bit different. And they are intersecting here at this location. And where is this location? -2, 4. That's our solution. Now, what does a solution mean? A solution means that if you plug this point into the first equation, where my y value is 4 and my x value is -2, I still have my -2 after that. I have 4 equals 6 minus 2, so 4 equals 4. That worked. They have to be equal when you test it. When you plug in the x and y, do you make a true statement? Now we can also do it with the other equation. 5 times -2 plus 2 times 4 should equal -2. -10 plus 8, that's -2 equals -2. Check. So we have checked it algebraically to see if our point works. So you can try this one. Go ahead, pause the video, then we'll work your way through it when you come back. So here, what we're going to do is take our first equation, which is 2x plus y equals 4. We'll subtract the 2x across. And we have it as negative 2x plus 4. So we're going to start at positive 4. And we'll do our slope of negative 2, positive 1. If your slope currently is not a fraction, you can just put it over 1 to make it a fraction. Negative 2, positive 1. Negative 2, positive 1. Then we'll come on down to our next equation. And we have 4x plus 2y equals 2. We'll subtract across our 4x. We'll divide by 2. Now we can go to our slope of, or our y-intercept of 1 and do a slope of negative 2 over 1. Connect those. And we notice that the lines do not intersect. They have the same slope. We have no solution. All right, we're going to come over here. And how many solutions are possible if we have one line and one parabola? What does that mean? Well, if we have a parabola, we could have a line that clearly intersects both. We could have a line that touches it at exactly one point. Or we could have a line that does not touch it at all. So we could still have 0, 1, or 2 solutions. What if we have a line and a circle? What's that going to look like? You're going to have a circle. What about the line? It could clearly go through it. What type of line do we call that goes through a circle twice in two different spots? It's called a secant. A secant goes through a circle twice. Now, a line can touch a circle exactly once. What do we call that? It is a tangent line. It's a line that touches a circle exactly once. It's a tangent. Or you might not touch at all. So those are your three solutions. You could have 0, 1, or 2 solutions. So let's look at this first example. What do we expect to happen with this first example? What shape is it? And how many solutions are we going to have? Let's look at the first equation. First equation. What type of equation is that? We all need to know. That is a circle. It has the x squared and the y squared. Do we need to do anything to this equation so it's in a format that we like it to be? We're going to add the 25 to both sides. Do we need to complete a square? Okay, we don't need to complete any squares. We already have an x squared and a y squared. We are all set. We don't have any b values. Nothing tricky in there. And we're not solving, so we're not going to take any square roots. That is the equation of a circle. So if that's our equation, what is our center of the circle? And what is the radius of the circle?
Oh, the radius is 5. Oh wait, the radius is 5.
We know the equation of a circle formula is x minus h squared plus y minus k squared equals r squared. Since we don't have any parentheses in here, we know that the h and k are both 0. And that determines your center. And because the radius squared is the value outside the equal sign, we have 25 as r squared, so radius is going to be 5. So now we can come on and plot our points for the origin. There's all our points that we can plot. Now, it's kind of cool. With the value of 5, you can actually go over 4 and up 3. And that's going to also be a total length of 5. Or you could go over 3 and up 4. And that's going to be a value of 5. It's kind of a fun fact using the 3, 4, 5 triangle. But that's not a requirement here. We're just going to go through and around the corners. Try to get as wide as you can, and you might have some sort of a decent circle. Here we're going up to the 5, and we're going to do a slope of -3. And we'll take our straight edge and connect those dots. There we have it. When we're talking about the radius and you're working with a number that is not a perfect square, like if it was 12, if we had the square root, or actually r squared that equal 12, we would need to take the square root of the 12. So then we would need to simplify that to call it 2 root 3. That would be the best answer that we could give for the radius. Now remember that when we take the square root of both sides, we're not considering the plus or minus. This is geometry. This is a length. Negative isn't going to be a length of a radius. So our R value is just a positive 2 root 6. Now to graph that, what is the value in terms of a distance? It's easier to come up to here to determine what the approximated value is. We know the square root of 16 would be 4, and the square root of 9 is 3. So the square root of 12 is actually a little bit closer to 9 than it is up to 16. So the square root of 12 is in between 3 and 4, just about in the middle. So if you were plotting something with a radius of 12, or square root of 12, we would come up just larger than 3 but less than 4, pretty close to 3.5. All right, we'll come on over to a parabola and a line. We know this is a parabola because we have a quantity squared. So if we were to multiply this out, we'd have to write out the parentheses twice and FOIL it together. You cannot distribute your 2 through. So you would get x squared plus 4x plus 4 and then subtract 3 more. Then you'd have it in standard form. We don't need to do that. We can graph it just the way it is. It's actually very handy. We're going to go 2 to the left and 3 down. There's your vertex. Now, what about the other points that belong on our parabola?
It's just a quadratic equation, so it should standard parabola going.
We would have our standard parabola, our parent function, coming up here because the a value is 1. So when we go over 1, how much do we go up? 1 squared. When we go over 2, how much do we go up? 2 squared, which is 4. When we go over 3, how much do we go up? 3 squared. And we can take all of those points and reflect it over our x-axis. Not our x-axis, sorry. Reflect it over our line of symmetry that goes right through the center. There's our parabola. And we didn't have to do all this additional math. We used the idea of the parent function, and we know that we were 1 over and 1 squared, 2 over 2 squared, 3 over 3 squared. And we're able to identify the points that are on our parabola. That is a. Now we're going to graph our linear equation. So we're going to have to move our x over. So we have x minus 1. So we go to negative 1. We draw in our slope of up 1 over 1. Up 1 over 1. And we graph our down 1's backwards 1, right on the dot. Right on the dot. So what are our solutions? How many times does this linear equation, linear graph, touch the parabola? Touches it 2 times. It touches here at negative 1, negative 2. And it touches over here at negative 2, negative 3. Touches at 2 spots. We could test this out to see algebraically, you could plug in a -1 for your x, add those two together, square it, and you get the answer of -2. And that's what we said here. When we plug in -1, we'd get a -2 for the y. So that's checking it. And you can check your other point that when you plug in a -1, you're going to get a -2. So both graphs exist right at this point of -1, -2. And the same would work out for -2, -3. How would we graph this parabola? Kind of do it a couple different ways. You have a lot of different tools now. One thing you can do is take your standard form and, if possible, you can factor it. Two numbers that multiply to be 8 and add to be 6. So when you solve it using the zero product property, you would be crossing at -2 and -4. If you want to use -b over 2a, you get a line of symmetry here at -3. So now we're going to plug our -3 back into our equation.
What is -b over 2a from?
When we calculated our -b over 2a, we got the value of -3, which was our line of symmetry. That was the value in between our two x-intercepts. So we have a y-intercept, or a y value of our vertex at -1, which is not a surprise, because isn't our parabola, if our a value is 1, isn't our parabola supposed to be over 1 up 1? Over 2 up how much? 4. And reflect it. Over 3 and up how much?
9.
Which is the same value as your y-intercept. 3 steps from the line of symmetry, 3 steps past your line of symmetry. So there's your parabola. Just a little reminder about graphing parabolas. We have this line, x equals -2. X equals -2 is a line that crosses the x-axis and we see that that's going to cross at -2, 0. And when you plug in -2 to your quadratic, you get 12 minus 12, which is 0. And that's what they say you'll get. All right, for us to check this out, let's see, example number 2. Example number 2 is here. So, for us to practice checking this, we go to y equals, and we would say x plus 2 squared minus 3. That's your parabola. And x minus 1, that's your linear equation. And we see that those go right through just like we graphed it. And if you go to your table, you can look where x was -1 and it has the same y value. And you can go to x is -2 and you can see you have the same y value. But everywhere else they have different y values between the two. So I typed them into my y equals. Those are the two equations we were talking about. And then I went to table to see what specific values matched up. And we got -1 and -2 to give us the same y value in both accounts. So that's the way you can tell if they actually cross. So we did that. All right, last one. Write a system of two unique linear equations with infinitely many solutions. So if you wrote one equation that had y equals x plus 2, you could say, and you wrote another equation that was a multiple of those, like 5y equals 5x plus 10, I times them both, everything by 5, then you would subtract over your 5 most likely, and you would say your equation was something like that. So graph this equation. That's easy to do. Graph this equation. Well, you have to convert it. You got to bring your 5x over. Then you would divide to get your y by itself, and you have the same exact equation. So that's when they say that all the points in the one equation are going to work in the other equation. It's an infinitely many solutions. And then our final one, write a system of equations of a circle and a line with no solution. So if we have a circle that's going to cross out here in the left, we could call that circle x plus 3 squared and y plus, let's say minus 4 squared with a radius that was pretty small. Let's just make it convenient. That's going to cross 3 to the left, 4 up with a very small radius. Now I want a line that's going to be over here. So that could be y equals a slope of x minus 1 or minus 2 or 0. Probably get away with 1 or 2.